Hello, fellow friends of Euclid, and welcome to the Geometry Chapter 2 practice test. We'll go through this quickly. You can pause the video anytime you want if you need more time to write something down or make a note to yourself. But here we have 3x equals x times 3. That's called the commutative property of multiplication. And you've known that for a long time. You've known 3 times 4 equals 4 times 3. This is just the fancy math name for it, and you have to know that term. And I'll abbreviate multiplication. And what is this? This is the identity for addition, part B, because when I add 0 to something, it does not change its value. Alright, so that's the identity, additive identity specifically. Alright, you have to follow order of operations, and that's what number 2 is about. They want you to see that 15 squared is 225. You have to do these exponents first. 9 squared is 81, so 225 minus 81 equals 144. Notice the difference between part A and part B. 15 minus 9 is 6. We have to do that because it's inside the parentheses first. And you know from PEMDAS, parentheses come first. So that's really 6 squared. 6 times 6, 36. Alright, and hopefully in number 3 now you identify these as like terms. They have the same variable raised to the same exponent. And you also remember that if there's no letter in front of, there's no coefficient, that's what we call the number in front of the variable, then there's a 1 there. So this is 7x cubed minus 1x cubed, so that is 6x cubed. I perform the mathematical operation on the coefficients, the numbers in front of the variable. Some of you may have put 7 because you thought x cubed minus x cubed would zero out. That's not how it works. Alright, part B. This is distributive property. When we have subtraction in between, and make sure that you get this because it's an easy thing to make a mistake with. Alright, so what we have to do here is we can drop the parentheses from this first one because we're going to distribute the subtraction through there. The easiest thing to remember is that look inside the second set of parentheses. Whatever signs you have in there become opposite. Okay, so I have a positive x, that's going to become the opposite of that. So it'll be minus x. And the plus sign becomes minus 2y. That's what is caused by this right here. That's subtraction in between, so you have to distribute it through the second set of parentheses. Now you can combine like terms. Okay, so when you do that, you see you have 3x and minus x. Always take the sign in front of this one to determine if you should be subtracting or adding when you do that. So that makes 2x. And then you've got a 2y here minus 2y here. Okay, so they'll zero out. So that'll leave you with just 2x. Alright, that's the algebra review that'll be on this test. So be aware of that. Alright, number 4, consider the definition. Circles are coplanar if and only if they lie in the same plane. Alright, so we have to be aware of this when we see it. It means we've got a definition going here and definitions are formed by taking two conditional statements and turning them using the conditional statement that's true and its converse that's true. Alright, so you can see what we've done here. I've taken these clauses that are on each side of the if and only if, and I've taken the first one and made it a conditional statement. If circles are coplanar, then they lie in the same plane. Alright, now write the converse. So if circles lie in the same plane, then they are coplanar. So we've had these two switch places. This is sort of if A, then B. And then we go on to if B, then A. That's converse, right? If A, then B. And if B, then A. Those are two conditional statements. One is the converse of the other. Alright, so I've identified the if and only if right here. And from each side of that, if circles are coplanar, then they lie in the same plane. And then I use the converse of that. So the hypothesis and conclusion trade places. If circles lie in the same plane, then they are coplanar. Part C, in this case, is the converse true? Why or why not? Well, yes, it has to be, because it's from a definition. Definitions are made up of a true conditional statement and its converse, which is also true. And so it's not automatic that a converse of a conditional statement is going to be true, but when you put them together in a definition, then both the original conditional statement and its converse have to be true. And so since we are told this is a definition, we know that it was made up of a true conditional statement and its converse, which is also true. Read the following statements carefully and mark them true or false. Alright, so here we've got a syllogism is an argument in the form of if A then B, if A then C, therefore if B then C. That's incorrect right there. So that makes that false. Alright, because it's supposed to be if A then C right there. Alright, so be aware of that. You know what a syllogism is, the standard form, if A then B, actually this should be if B then C, therefore if A then C. So there's two mistakes in that one. B, if the radius of a circle is r, its circumference is pi r squared. Trick question. No, not the circumference. Circumference is 2 pi r, or pi times diameter. This is the area formula. Okay, so if we had changed this word to area, it would be true, but because it says circumference, it's false. Alright, and then to prove a theorem indirectly, we begin by assuming that the opposite of its conclusion is true. Yes, that's right from our reading. That is true. Opposite of its conclusion is true. We suppose that the opposite of the conclusion is true. Alright, what is this type of figure called? I think all of you know. It is called an Euler diagram. And the standard way to read these is as a conditional statement from the inside out. So write this statement in if A then B form. If she speaks Spanish and English, then she is bilingual. You can see that we've got that here. Alright, and that's pretty much, everyone should know how to do that by now. Part C says rewrite in the form B if A. It's easy to misread this because we're used to having it only in the standard form here of the conditional statement, or its converse. That's what you're used to dealing with in conditional statements. But this is a little bit different. B if A. Okay, so what was B? B is that she is bilingual. A is that she speaks Spanish. So if I recognize that and I say she is bilingual if she speaks Spanish and English. And it's very important that you write it the way it says, with if in the middle. Alright, part D, which of the following statements is also illustrated by this diagram? Okay, you know that we read this from the inside out, but if we negate the hypothesis and the conclusion and read it outside in, that is also true. So which one of these three statements negates or says the opposite of and reads it outside in? If she is not bilingual, that's outside. Okay. She does not speak Spanish or English. Number 2 does. Okay, so be aware of that. The Euler diagram will show two of our true statements. Conditional statement, if she speaks Spanish and English, then she is bilingual, or the negation of that reading in the opposite direction. If she is not bilingual, then she does not speak Spanish and English. Considering the following argument, if this is a direct proof, then this is not an indirect proof. If this is not an indirect proof, then there is no contradiction. Therefore, if this is a direct proof, then there is no contradiction. As you can see, I've marked A, B, B, C, A, C. What are the premises of the above argument? Remember premises from the syllogism. I'm giving it away a little bit here. Are if A then B, and if B then C. Well, if you see how this is marked, you can see that's right there. If this is a direct proof, then this is not an indirect proof. Okay, that's the first premise. The second premise is right here. If this is not if this is not an indirect proof, sorry about that, an indirect proof, then there is no contradiction. Okay? So what is the conclusion? If A, then C is the conclusion. Here's A, here's C. If this is a direct proof, then there is no contradiction. Is the argument a syllogism? Yes, it is. It fits the classic syllogism. So there it is. In the figure above, DEF is a triangle. Tell whether each of the following statements is true or false. Points D, G, and E are collinear. Are they collinear? Yes. You can see they are collinear. So that's true. On the same line. Alright, points E and H determine a line. Well, let's postulate 1. 2 points determine a line. Those are 2 points, and they determine a line. So that's true. Okay, and then we have points F, H, and E are coplanar. Where are F, H, and E? Well, here they are, right here. Yeah, they're coplanar. You can say they're on the same plane. That's true. But this is where people get confused. They get confused between C and D. Points F, H, and E determine a plane. How do we determine a plane? Postulate 2. 3 non-collinear points determine a plane. Are these F, H, and E non-collinear? No, they are collinear. So while they are on a plane, in fact they're on many different planes, they don't determine a single plane, so that's false. Points D, G, and F determine a plane. D, G, and F. These are non-collinear points. 3 of them are not on the same line. So that is true. All right. So there's some true-false for you. Number 9. After studying the relations of the statements given the following proof, write the missing statements. Here's the theorem right here. If a group of chess players checked into a hotel, the manager would say, "I can't stand chestnuts boasting in an open foyer." What is the first statement? Well, where are we going to get that from? Well, we know the first statement's got to start with the hypothesis of the theorem here. If a group of chess players checked into a hotel, how do we get the second statement? We look after this first statement. They sit in the lobby bragging about their tournament victories. So we would say, if a group of chess players checked into a hotel, then they would stand in the lobby bragging about their tournament victories. How do we know that? Because remember that each succeeding conditional statement begins with the conclusion of the previous statement. So since we know that, this is the next statement right here, that has to be the conclusion of the previous statement. Alright, that's where we get that from. So if they stood in the lobby bragging about their tournament victories, the manager would ask them to leave. What is the third statement? Well, remember, it's got to start out with the same thing that the last one finished with. So the conclusion of the last statement becomes the hypothesis of the next one. The manager would ask them to leave. So if the manager would ask them to leave, they would ask why. Right there. If they asked why, the manager would say, "I can't stand chestnuts boasting in an open foyer." you can see that it finishes with the conclusion of the theorem up here. And that's the way they are. In what kind of proof does this happen? Well, we only know two kinds right now, direct and indirect. This is a direct proof. Continuing to reason from previously proved statements, previously given statements. Right? So remember how an indirect proof starts. It starts by saying that we can start with the opposite of the conclusion, supposing the opposite of the conclusion. So if we were going to do this as an indirect proof, we would have to start, here's the conclusion of the theorem, right? I can't stand chestnuts boasting in an open foyer. So that was an indirect proof. If we were going to do this as an indirect proof, it would start with, suppose I can stand chestnuts boasting in an open foyer. And then remember that would reason until we found a contradiction, and then we would be able to go back and conclude, yeah, that's right, I can't stand chestnuts boasting in an open foyer. But that, I just say that to you, it has nothing to do with this problem, that information I gave you about the indirect proof, but just to show you a little bit, highlight the difference of how an indirect proof would work. Alright, in this figure, squares have been drawn on the sides of right triangles given A equals 8 and C equals 17. Find, and then they gave us some things to find. I copied this figure onto here. You saw it the other day. Here's a right triangle with side lengths 3, 4, and 5, and squares built on the sides of that right triangle. Here's one with an area of 9, here's one with an area of 16, and here's one with an area of 25. And you must know that the two small ones that are built on the legs of the right triangle have the sum of their areas equals the area of the larger square built on the hypotenuse. So if I know 2 out of the 3 areas here, if I know 2 out of the 3, I should be able to figure out the third. Alright, so let's mark this other figure up, given that A equals 8. Okay, so this is 8. And C equals 17. C equals 17. Alright, find the area of square A. Well, A has a side length of 8, so 8 squared would be 64. So it's 64. And then it says, find the area of square C. Well, square C has got a side length of 17 here, so 17 squared is 289. So that's 289. Alright? Find the area of square B. Alright, remember that it's this square plus this square. Their areas added together equal the area of this larger one right here. Okay, so I know the larger one and one of the smaller ones. So I'm going to do 289 minus 64 to find the area of square B. And I'm subtracting because I know the larger one. This one and this one have to add up to the third one. So 225. And then it says, find the length of this square there. Find B. Well, how did we get the area? How would we get the area? We would take the side length squared. So we would say the side of that squared. In this case, it would equal the area. So in this case, we would have B squared equals 225. How do you undo squaring? By square rooting. Square root of 225 is 15. Okay, so we know that the side length B is 15. Alright, keep in mind this relationship here. That will help you answer these. The figure below appeared in a problem on an SAT exam. Find each of the following. Angle ACB. That's this angle right here. And that is, it looks like it's x degrees plus x degrees. Now, here's the thing you have to do in geometry to be successful in this course. you're going to have to start seeing figures inside of figures. Most of you will focus on this triangle right here, and this triangle right here. How many of you will see that there's also the large triangle? Triangle ABC, which I'm outlining in red. Triangle angle sum theorem says that the three angles of a triangle will add up to 180. I know two of the angles of this large triangle I've outlined in red. One of them is 30, one of them is 45. And I know that when I take this third angle here and add it in, they have to equal 180. So, if I take away 45 out of that 180, and then take away 30, I see that angle ABC has got to be 105 degrees. So then what's x? Well, here's what you've got. 2x equals 105. And you know how to solve that. Right? So it's 52.5 degrees. And 52.5. Okay? So what is angle ADC then? It helps a lot if you will mark up your figure as you come up with information. Then you'll be able to see relationships so much better. Where's angle ADC? It's this one right here, isn't it? Yeah, it's right here. Okay, so now I go back to seeing the smaller triangle, triangle ACD, which is outlined in green. I see I've got a 45 and a 52.5. Okay, so I've got the two that I know add up to 97.5, so then we just subtract that from 180, and you get 82.5, so it's 82.5 degrees. Given that the that's it for number 11. Number 12, given the circumference of a bicycle wheel is 2 feet, find its diameter to the nearest tenth of an inch. Alright, what's the key piece of this one? First key piece is you have to see that they gave you units in inches or in feet, and they want answer in inches. Alright, so that requires a bit of a conversion here. 2 feet equals 24 inches, right? Okay. Now, you know that circumference equals pi times diameter. So what information do I have here? I have that the circumference is 24 inches, and I'm supposed to find the diameter. So I want to isolate d, find d, so we'll divide by pi on both sides. So we get our answer by 24 divided by pi. Alright, now if you do that, you get approximately 7.6 inches. Now the mistake some of you might make on the test, and maybe you made on this one, is you don't catch this, feet, inches. Make your conversion first. And then just use circumference equals pi times diameter to figure out the diameter. Alright, so how far does the distance travel? What is the distance that the wheel travels in making 11 revolutions? 11 full revolutions. You might not know this, but when a wheel goes around, like your bicycle wheel, when it makes one complete revolution, the distance that it moves the bicycle is the circumference. So every time that this goes around once, it moves it 24 inches, because that's the circumference, or 2 feet if you have it in feet. So 24 revolutions, 24 for the circumference times 11 revolutions, and that equals 264 inches. Or you don't have to do it that way. You know that the circumference is 2 feet, so you could just put it in feet. Here you have the freedom to do it either way because they did not specify which it should be. So there are actually two answers that would be acceptable here, in inches and in feet. There you go. Either one of those is fine. Okay, that's this practice test in a nutshell. So good luck to you. Make sure you make some good notes. Use this as a study. Have a geometric night. We'll see you for the test.